All right, take it away for the first part here. And welcome
All
back.
right. Welcome everyone. Welcome to your second lesson of your cult onboarding. I'm excited to teach you about irregular syntax and other fun stuff today. So let me share my screen. All right. Can you guys see my screen clearly?
Yeah.
All right. So what is irregular syntax and why is it important? So let's look at a simple example from last class. So you see this tree here with this senhep, add, colhep, 5, 6. And can anyone remind me what these runes do and what this tree structure is going to compile to? I should open the chat. Yep, seeing some correct answers. Yep. So colhep is going to make 5, 6 into a cell, and then the senhep is going to run the gate add on that cell, and it's going to get you 11. All right, so here's something a bit more complicated. Can someone tell me what this is going to do and what you're going to get as an output of this?
Is there one and only one order of execution here?
Yeah, so basically you're gonna reduce from the bottom up.
Okay, but is it like depth first or breadth first? So you start like 3, 5 become.
It is depth first, but there's some discussion about potentially changing that in a future version of Hoon.
Okay.
So for all those that are unfamiliar with that reference, are we saying that the furthest right side of the tree executes first? Is that the same? Is that what that means?
We're saying the deepest part of the tree evaluates first.
Okay.
So this goes back to when we were talking about evaluating things right to left when we read them on the command line.
Yep.
Yeah, so basically, like, if you look at the subtree for the add, well, you can't evaluate the add until you evaluate this colhep 3, 5.
Checks.
You can't evaluate this mole at the top until you evaluate what the sub and the add is doing. So you're gonna have to, it kind of forces you to go depth first, basically.
So the 3, 5, so you have a node, or sorry, not a node, a cell is constructed with the 3, 5.
Yeah.
And then is the next operation the add operation, or is the next operation the 4, 2 cell construction?
Yeah, it actually doesn't matter. But you can, I think in
He got
you
it.
add first, and then you can collapse this to the 8, and then you can look at and then you can't evaluate the mole yet, so then you'd evaluate this subtree. But yeah, I saw a correct answer in the chat. So is everyone kind of clear on what you're gonna get if you evaluate this?
Yeah, it makes sense.
Yeah, it makes sense. Okay,
Yep.
good stuff. So the reason I'm bringing these to your attention is because every Hoon computation and the underlying knot computation is simply about applying rules to transform binary trees. So when you're doing this in your head, or when you're just doing like add 5, 6, like anything you see in Hoon is doing something fundamentally similar to that, where you're collapsing the trees and applying these reduction rules to it. So that's kind of like the core essence of what's going on. However, it's totally impractical to write your code as raw binary tree manipulation. So that's the whole point of what we call irregular syntax or sugar syntax. Sugar syntax is basically a way to write raw machine-like code in a way that's much easier to read and manipulate. Yeah, I see a raised hand.
Yeah, you called mul and sub and add. You called these gates. Why are they
Yes.
called gates?
That's like Hoon terminology for a function, basically. Yeah, we'll get to that later. Gates is something we'll actually be covering in this lesson. So
Okay, I mean, but is there like an intuition behind that? Like the
Behind-
rune names I can understand. But gate, it just seems kind of arbitrary.
yeah, so Neil will cover what gates are and why that name kind of makes sense in the latter half of the lesson.
To the extent it makes sense, but yes.
So we were saying we use sugar syntax / irregular syntax to make this binary tree structure more readable, more usable, more programmable for the user. And actually, all of Hoon can be thought of as sugar syntax over the underlying knock, and the underlying knock is going to look something like this, which is just, you know, binary trees and numbers and integers, basically. Okay, so going back to something more simple. So we learned that this col-hep is going to make a cell of this 1 and 2, and you can write it as col-hep 1, 2, or you can just write it as the cell, right? And those are equivalent. Now, what if I want to write a triple? What am I going to have to do if I want to store a triple of 1, 2, 3 in a binary tree? Well, I'll actually have to store it something like this. And can anyone tell me what this is going to look like written in the cell format?
Cell within cells, a
Yep,
cell within a cell.
yep. I see. Yep, some right answers. Yep. So if I type this in the dojo, 1, 2, 3, then it's going to reduce to this. So that's our first bit of sugar syntax that we're learning, is that when you have a triple of 1, 2, 3, it's actually this underneath. What if I want to do a quadruple, 1, 2, 3, 4? What's that going to look like in the cell syntax? Yep. See some right answers? Yep. Oh, top phosphorus, that's not exactly right, but you almost got it. Because your top level thing is a triple there. Yeah, so basically if I do 1, 2, 3, 4, oops, then that's going to give me a quadruple. All right. So something particularly interesting. Oh, and I forgot. So with the triple, there's also a rune. So you can do col-lus 1, 2, 3, and that also is equivalent. And you can, for the quadruple, there's also a rune. 1, 2, 3, 4, and that makes your quadruple. So if I take that quadruple from the last image and I replace the 4 with the sig, then we get this structure. And this is what we call a null terminated tuple. And this is going to be an important concept later on, because lists in Hoon are actually null terminated tuples. So it's just going to be a tuple and the sig at the end. All right. So here we're going to get to a really important example of sugar syntax. So we've been calling add with this senhep add colhep 1, 2, and that gets us 3. And we can sugar the cell to get add and a cell of 1 and 2, right? But something else that we can do is we can actually just use these parentheses like this. And this is sugar syntax for that senhep, that function call. So you guys feel free to try that out yourselves. And something else we can do to make this even nicer to read is we can use this send less rune, which instead of passing the arguments to add as a cell, we can pass in 2 individual arguments. So like that. And we can trigger that with the parentheses as well to get add 1, 2. And that's actually the most neat and most very commonly used way to just call a gate, which is just like this, add 1, 2. All right. So let's talk about auras. So last lesson, we were introduced to auras, and to remind you, we have an underlying integer, like say 1, and then we can cast it to a pat p, right? So this underlying 1 is just interpreted in different ways. So if we interpret it as a pat p, then we get nec. We can also interpret it as a pat ub and a binary, and we get this 0b1. And we can also interpret it as a date. And we get some time really long ago in the past. And the point is, you can do all sorts of auras with this, right? And the reason it's important to understand auras is because Hoon programs are going to enforce certain auras or certain types as inputs and certain types as outputs. So let's say I'm writing an app to make a discussion forum, and the discussion forum is going to say, it's going to need who posted this, what's their pat p, right? So you got to return that data as a pat p rather than just a big integer. Then it's going to ask for what's the date this was posted. That's going to be the date format, right? And it's going to ask for the text of their post, and that's going to be a text format. We have to return these as the correct formats rather than as just big integers. And something that'll help us, a useful tool for this is this rune called kethep. So this is also called a fence. And it enforces that basically you have some Hoon on the right side and an aura or a mold, which we'll talk about later, on the left side. And it's going to say whatever comes out of this Hoon has to match this aura. I see a question. Is there an equivalent of clear? I don't fully understand what that means.
Like the Unix command to clear the terminal.
Oh yeah, there probably is, but I was
Control L.
Control.
Okay. I don't mean for you, I just mean for me. All right, thanks.
Okay, cool. But yeah, so kethep enforces the Hoon matches this aura, right? So here's an example. We can do kethep space pat ud 1, and that's just going to return the 1 because it's saying yes, this 1 matches the pat ud. But if we do like this, kethep pat p 1, then it's going to give us an error because the 1 doesn't match the pat p, right? And here's something a bit more complicated, a bit closer to what's going to happen in real Hoon code. Okay. So maybe you guys take a look at this and figure out what's happening. But the equivalent code is here. I'll put it in the chat as well. You can try that out. But basically, so in this lowest subtree, we have this cell of 3, 5, and then we're going to add them, right? And then we have this kethep here, which is saying whatever comes out of this subtree, it has to match pat ud. So in this case, we're doing add on 3, 5. We're going to give it an 8, and the 8 is going to correctly match this pat ud on the left. And then this fence is going to be like, okay, that's good, and it's just going to kick that 8 up. This whole subtree is going to become an 8, and then you're going to do mul 2, 8, and then we'll get 16. Right? Does that make sense to everybody?
Yep.
All right, great, good stuff. Now what happens if we change this code? So we have something else here. Introducing a gate called weld. All you need to know right now is this is just going to combine these 2 text strings into 1 text string. So what's going to happen, right? We have this A, B, C, D, E, F. They're going to get welded together, but right here, it's going to say, hey, this is some text, and this enforces a pat ud, so it's going to throw you an error right there. Yep, exactly. So that's basically that's why we use ketheps, is to enforce that what's coming out of some code is a correct type, and they're super useful for just putting throughout your Hoon code to make it be correct, help you as a coder. So yeah, so we just talked about ket-hep and auras, right? And auras are like what is the type of an atom, but there's a lot more complex types in Hoon. So the first notion of type is going to be the aura, which applies to atoms. And the next notion of type that we should consider is going to be called molds. So if atoms is like a chemical atom, then molds are like molecules. And you can have a really simple molecule like water molecule, or a really complex molecule like a piece of DNA. But the point is that you can build molds out of atoms in various ways. All right. So there's a few runes that you can use to make these more complex types. So the first one is going to be it's called buck what. So here what's going on is we're making a type union. So we're saying my mold is something that can be either a pat P or a pat T. So if we do this code here, and then we feed Zod to my mold, and it's just going to return Zod because the Zod is one of these. And we can also feed it some text, pat T. And actually, because of a funny quirk of the compiler, it's actually going to convert this to a pat P. But the point is that it did not fail, so it says this is correct in code. But what if we do this? Then we give it a 1, and it's going to fail, right? Because this pat UD is not one of pat P or pat T, right? Does that make sense to everyone?
Makes sense.
Okay, good.
But I mean, there's a quirk with the compiler you mentioned.
Yeah, maybe Neil can explain that more, but
Uh-huh.
basically, like when I did like right here, I did my mold and then I fed it this ABC. Like I guess ideally you would just want it to spit out ABC, but it actually converted this ABC to a pat P. Like this.
Oh, yeah. This is what's happening is that molds, harkening back to the analogy that Jack mentioned a moment ago about molds being, or simple atoms being like atoms and molds being more complicated structures. The type union buckwhat that he introduced here that lets you choose between two different types actually can't really tell the difference between atom types, aura types. It's not exactly a bug for deep reasons in the type system, but it's not expected behavior. And it does much better when you're trying to distinguish two things that are structurally different rather than two things that look like have the same shape. So it's, in some ways, it's better if you're going to lean on the atom and molecule mental model to always think of a type union or molds as letting you distinguish the structure of things. So things that are like a cell that is a pair of two atoms from a single atom, that would be trivial for this to do correctly, for instance.
Thanks.
All right, so moving on, here we saw some examples of using this mold with the ket-hep, right? But you can actually also use a mold as a gate. So if I do like this, and then I do my mold Zod, then it's gonna spit out Zod because like applying this transformation to Zod results in Zod. But what if I do this? So this is different than before. What do you guys think is gonna happen if I press enter? Is it gonna fail or is it gonna do something? And what is it gonna do?
It's gonna fail.
Yeah, so the interesting thing is actually this is not gonna fail.
Gonna construct a pat P.
Yes, yeah, so if I press enter right here, it's actually gonna turn that 100 into a
Mm.
pat. So that's a difference of using the mold this way as a gate
Mm.
versus using it with the ket hep. Does that make sense to everybody? Okay. So so the next rune that we're gonna learn for making molds is called buck coal. So buck coal, so the last one we did type union, so it can be this or this or this. Now this one is actually like, let me make a cell of like, it has to be this in the first place and that in the second place, or however many places. So like, suppose I'm making an app that's like a simple bank on Urbit, right? So some information you might want to have is here's somebody's pat P and here's how much money they have, right? So I can make a simple data structure for this, like so. And then I can apply it to this cell of sample palnet and 100. And it's going to validate that indeed this data does match this data structure. Does that make sense to everyone? All right, cool. All right, so that's basically a short description of this buck coal. The next thing we're going to learn about is called bunting. So if you have an aura or a mold, you might want to get an example value for it. So the rune you use to do that is ketar. And so if I run ketar pat ud, it's going to give me a 0 because 0 is the default value of a pat ud. And I can also use it on the mold as well. So if I do this bank data again, and then I can do ketar bank data, and that's going to give me a default value for this mold that I created, and it's going to use the default values for pat P and pat UD to do that. So here just filled in ship equals odd and money equals 0. And finally, there's also a sugar syntax for this. So if I do this and I just do tar bank data, then that'll do the same thing as well. All right, so an important thing for molds is these mold constructors. So an important example one is list. So if I do like list pat UD, that constructs a mold, which is a list of pat UDs. So I can use this in the following way. I can do ket hep list pat UD 1, 2, 3 sig, and that's just going to enforce that yes, this matches the mold of the list pat UD. If I take out the sig, it's going to complain because now it doesn't match what the list looks like. And I can also do a typecast like that. So yeah. And then the final thing about molds and auras is we can identify them. If you have a noun that you're not sure what it is, then you can use this rune called Zapgar. So if I do Zapgar, this thing, then it's going to give me a cell of 2 things. So this is called a vase. We'll learn about this later. But basically, all you have to worry about right now is this first entry of this cell that's created. That's going to tell you what type this is, basically. And we can use this thing called the type sphere here. So, and then that's just going to directly grab that type information. So yeah, I think that concludes my part of the lesson. Were there any questions on anything?
One question on the default values.
Yeah.
So let's say we want to default to be like a null instead of a 0.
Yeah.
Is that like possible at all, or is it just always going to be defaulting to 0?
Yeah, I believe Right, so there are rooms where you can make a mold and then you can set it to have a default value that's other than,
The
like,
standard defaults.
yeah, and Neil will be more clear on this, but yes, that's possible, yeah,
Okay, cool.
yeah.
One example of a place where you end up wanting that is, if you're going to do a summation, then you want your summation to start from 0. So if you're going to apply add more than once to something, you want it to start counting from 0, of course. With multiplication, you actually don't want it to start from a default value of 0. You want it to start from a default value of 1, because otherwise, of course, mole times 0 is going to drop out. So I can show you an example of this in just a moment. Jack, can you make me host again real quick?
Yep.
Should be in, yeah. Okay. All right, power's back going to my head again. And I think this is the right one. Does that look right? That looks right. All right, let me move some things out of the way so you can actually see the screen. And let me keep the chat open. All right, so we're introducing new runes as we work through this in a way that will hopefully help you solve the problems that you're running into, in a sense, because we're giving questions to you, right? This is the trouble of starting to learn new languages. We start giving you assignments to work through, and we're going to pace these things and move them around. Such that the homework will mostly rely on the lesson notes, but we may occasionally introduce a new concept briefly in the homework, maybe with a little bit of explanation that's kind of previewing where we're headed in the next week. And one of these concepts that we've kind of run into, at least the necessity for some part of the solution, is we had you start using TISFAS and WhatCol here. So WhatCol lets you make a decision on the basis of a yes or no question, a true or false question. And so TISFAS let us define a value, which was then utilized when we did this call right here. And so this is the shorthand form of what would be the same thing written with senhep and then brackets like that, if we were to write it in the form that we've been using previously. We're going to start using the irregular syntax like this more often, but one of the things to keep in mind is that, of course, this always has an underlying runic form that gives you the tree structure of the code and lets you think very rigorously about what's going on. Anyway, so what we're asking here in this program is whether or not this value is greater than 1. So we're assigning some value 5 to it with the name A. We come down here and we know that this is going to be a senhep, and it's going to take as its first argument a name for something. Well, Jack mentioned that the thing that it needs is what we call a gate, right? And then the second thing are the arguments, the parameters that are handed to the gate, the values that we actually give to the gate. And so it first checks and says, do I know about a name A? Do I know about a thing called A? And if I do, then I can plug that value and I can replace that name with the value that's affiliated with that name. And then we can drop that in and we can run through all of this. So when I actually run this code one at a time, then it evaluates all these things and then it spits out, yes, 5 is greater than 1. Now, there's a couple of things going on here that have been left implicit up to this point. One of them is that every time we need to do some calculation, we have to build it from scratch in Dojo, right? Like we're actually having to type code. We haven't learned how to save code or load code or do anything else with it. And so obviously typing out a calculation every time we want to do it is not viable for anything that's not trivial. The other is we don't have any way of setting up a calculation for a value that is as yet not known, right? If I wanted to define this code here at the end, this decision, but I'm saying I don't yet know what the name A is. I don't know what that value is going to be. Then I have to have a way of deferring that decision or deferring that computation. So I can set up a computation, a calculation structurally, and then I can carry that around. I can give it a name. I can do something with it until I need to actually use it. So different programming languages have handled this idea different ways, and this is reflected in some of the names that this kind of functionality is given. In computer science today, we generally just call this a function, particularly leaning on things like JavaScript and Python. That's become basically the universal name for this kind of operation. It's also called a subroutine or a subprocedure, and a few other things in the older literature, but it essentially describes some block of code that can be supplied values and then called on demand. It's not, it's not pre-calculated for you. It's awaiting a particular value. One of the problems with the name function, even though a lot of computer science uses it, is that it always evokes a mathematical function. And in a mathematical function, you have a very clear definition of one or many inputs yielding a single valued output. And that it always behaves in this particular way. For whatever reason, the decision was made in Hoon to call this kind of thing, a subroutine, a function, whatever you have, a gate. So we're going to be able to build a Hoon expression now as a gate, and then we're going to be able to use it later on, perhaps many times. And so if we wanted to take the same code and write a gate that carried out the same calculation, it would look like this last block here that I've highlighted. Now, let's compare it to what we had just a moment ago, which would probably, okay, there we go. All right, again, I'm highlighting this code. So what changes between my TISFAS version that I was evaluating the dojo a moment ago and the way I've expressed the deferred calculation here? And you can even compare this to other programming languages if you know some well, right? Does it have a name? Does it have a return value? What does each line do? So first off, like, what's different between this code and the code above it?
The part is.
All right, so I have a line specifying, sorry?
The part is.
So I have a bar tis rune. So I'm using a different rune, and I'm specifying the type, and then I'm not giving it a value. Right. So this, essentially this is an input, right? It's this thing that we're going to utilize when we actually carry this around. We are going to call this the, that's a bad color scheme for that kind of drag. There we go. So this is our argument, or our specification. This is what our gate, our function is actually taking in. In this case, we're specifying that it needs to take in a PAT-UD, which is an unsigned decimal atom. If we give this anything else, this code will fail, right? We won't be able to evaluate it. Does this gate or function have a name? All right, so if we run in some programming languages like Python or C++ or whatever, we give functions a name at the beginning. This function doesn't have a name. So we have a function. We can talk about it. We can identify, the kind of thing that it returns, the way that it's behaving. We can even specify a little bit more. Jack mentioned a moment ago that we could also use like a cat hef as a fence, what we call the fence. So it's very common for the second line in your gate to be the return type, just so you have this explicitly annotated at the beginning of what's going on here. So what's my return type out of this function, out of this gate? What's the kind of thing that's going to be returned from it? Okay, so this will be a pat T, right? Yeah, so it is a string, but the in Hoon definition here is a pat T. And that's actually because there's more than one kind of string. So in Hoon, to say a string is not determinative of like what exactly is a string. Like you run into this in C++, for instance, where you say a string and you mean like, is this like a W car T thing? Is this like a character array? Like what exactly is this thing? So it's similar here. Right, so it's pat T because the value that's, we're going to be careful about the word output here. Just because output can be ambiguous. So it's returned by the function, the value returned by the function has the type pat T. It is a text atom. Output can also mean something that just gets printed to the screen. All this stuff we have up here, of course, is output of some kind or other. In this case, because I had done the calculation at the Dojo prompt, when the calculation completed, the result of that calculation was also output to the screen. But we have to maintain a distinction because sometimes we want to print something to the screen, we want to show it, and that's not the same thing as returning it from a function. It's just that in the Dojo, those actually do correspond to the same thing, which is, it's a problem with using REPL interfaces in general, but that's okay. All right. So what we have here is we have an input specification, we have an output specification, which is optional. This line is optional. And then we have the actual expression, right? The actual code, and it's a complete expression, right? It's an entire tree. There's no room with a hanging child that isn't dealt with. I know some of you ran into that when you were solving the boxcar function problem, where you had to think about there was a what call and then there was a what call inside of a what call. So you actually had 3 cases that you had to define, right? If you only define 2 of those because you forgot about it, then there was this hanging case that you hadn't dealt with yet. So you have to think through the tree structure whenever you do this. All right. So I'm going to copy this and give this to you in the chat just so you have some version of that. Again, if you go to the right-hand side and hit the 3 dots next to my text and hit copy, it seems to have a better track record with correctly preserving spaces. And since 2 spaces are different than 1 space in Hoon, that's a thing to make sure you get right. Now, Dojo gives me a way of attaching a name to this. We're not going to use this all the time. This is a Dojo specific convention, so we will come back to this. So I'm going to call this greater than -1. And then I'm going to write my code after it. And if I did it correctly, that should work. Okay. So this is a Dojo convention. I can attach a name to anything, but in this case, to a gate, to a function, by doing tis and then a name, and then whatever code comes after that here. And then, as you might suspect, I can give it a value and it should do this calculation for me. What's the other way I can write this calculation now? Talk me through it. If I wanted to do this with sugar syntax, what would I write?
In brackets. Oh, sorry, what is it called?
Okay. Yep. So we do parentheses here. Those brackets would give us a cell. Now, we actually could do it in brackets. This is kind of an interesting thing. And it's going to grind on this because there's something big. Yeah, so it's big, right? It's actually outputting everything. So it turns out that Hoon will let me do something like talk about a function, a gate, without any other information, right? I can talk about it. I won't do it with greater than 1 again because this is including all this junk that's in my Dojo right now. But if I do just like greater than by itself, it shows me some information about the greater than function. It gives me some information about the version of Hoon that my system is currently running, which is Hoon 139 Kelvin, counting down. It gives me some information about what the input arguments are. So what does greater than expect? Greater than 1 was one I just defined using just like this, but I did this syntax to greater than 1, single space after it, and then the rest of the function. So that'll give it to you in the dojo. So that's one that I just created. I'm in my screen manager, so I can't scroll as easily as I could otherwise. Now, there's also some interesting things that can happen because I can say things like, I can say greater than 4, and then this gets mad at me, right? Like it actually gives me an error and it says, okay, I don't know what to do with this, right? It doesn't have the right shape. It's not the right kind of thing. And so this is going back to what Jack was talking about a moment ago. That's because this specification that we're carrying around here is a mold, right? It is a type. It is a compound type. In this case, it's a simple compound type because there's only one element in it. It only accepts one atom for greater than 1, but greater than itself, right? Like GTH, less than LTH will have the same form. Add will have the same form. Mole, all these will have the same form. These actually need you to match the structure of what they're trying to do. Now, it turns out that there's more than one way to build and express things, as with many programming languages. So, so Jack was showing you, we could build a cell, a compound cell like this, and then we would get a cell inside of a cell. And we can use colas, which accepts 3 children and builds them into a cell the same way, right? So this is an equivalent other alternative way of stating this. So there are also different runes other than senhep that will evaluate a particular function. So if I were to give this, let me see if I can get this to work. All right, add 0, 0. All right, so senhep expects the name of a gate. So in other words, the name of something that that's a bar tiz and then has a specification with it. That's what it's looking for here. We'll get into more about like, what is this bar tiz rune? For right now, a bar tiz rune means that we're defining something that has a type specification for an input and an expression that uses it. That's all we're saying with the bar tiz right now. Bar tiz are actually saying more than this, but it doesn't matter yet. It'll matter in about 2 weeks when we get deeper into it. Right now, it's a simple function definition. There's also, let's see, there's like sen, I'm trying to remember what these are offhand. Yes, so senless, how many children does senless have?
Three.
It has 3. Because it takes the name of the thing, and then presumptively it is useful for things that expect 2 arguments. And so it's an equivalent way of stating the same thing. So if I were to say, senless add 1, 2 like this, then it actually leaves me hanging and it's saying, where's my 3rd argument? Right? Like what else am I looking for? And if I press enter or backspace, then Dojo throws away the calculation and doesn't finish it there. So there's going to be a lot of equivalent ways of writing these things. One of the interesting things is that, let's see if I'm doing this offhand, let me try this one. What is it Centaur? I'm trying to remember what parentheses actually resolve to in the general case. Because this is in response to the question earlier about how do you define a different default value for a gate, for instance. So this is like basically saying there's an add gate somewhere, there's an add function somewhere in Hoon. We could go look at it, we could see how it's structured, but it's going to use the regular bunt value, the regular default value of its arguments, which are these values, right? These are exactly what we expect here. Multiplication, if we call it by itself, we can see that it's starting from 1. And so it's actually defining things slightly differently, where it is using 1 as the default value rather than 0 as the default value, for the reason I said earlier about what's going on there. One of the interesting things about working with Hoon this way is that a type in Hoon is also a gate. Okay, it is also a function, which means that I can write expressions like this, where I'm saying apply this mold, apply this atom type, in this case, to this value, and give me the result of doing that. And depending on what I'm doing, I can actually write fairly complex statements that will let me do this sort of thing. I can use it to attach names to things as I keep working with them. Let's see, we did the Jack, you covered buck coal briefly, didn't you? I think we covered buck coal. Named tuple, is that right? I think we mentioned that. So this is one where we can, we can associate names with something. Okay, so Daniel Vortex, let me finish the example I'm on real quick, and let me come back to the Pat UX 6 example, because there's actually a subtlety there that it's a little bit different that I want to get to. But I want to see if this one works correctly first. Yeah, so this is one where what I'm actually building here is a mold, and this mold is going to operate on 2 values. But what it's going to do with those 2 values is, if they nest inside of Pat P and they nest inside of Pat UD, it's going to apply those to them, and it's going to give them these names. And so then once I have a one way, so I can we call this result. Write it this way. So now I can resolve ship against result, and I can look inside of result and pull the value named ship out of that value. So I've attached names to it using this named tuple, this named mold type. And now I can talk about names of things inside of other things that also have names. So when you start building libraries or compound functions and so forth, which we will lean more into doing over the next while, this is something that will resolve more things for you and give you expressive ways of accessing these pieces here. Now, one question was essentially, let me copy the text of this question and just put it down here on the screen, because this is an important question. All right, are Pat UX with the tick 6 and Pal UX A6 par, are these equivalent to each other? Okay, so in one case, what's happening here is we're taking some value and we're saying, like make this conversion. What the tick notation, it's also sugar, and what it actually desugars to is Pat UX Pat 6. So what happens in this case is that it explicitly removes ARA information from whatever's on the right. So I could do it with a ship name, for instance. It removes that ARA information. And then it converts it to the unsigned hexadecimal format. It's not picky. It will do that with anything. When I apply a name as when I apply an ARA here as a mold, then what it's actually doing is it ends up being an equivalent operation, but it's not doing it the same way. In this case, what it's doing is it's saying, basically, PAT-UX is a gate that can accept an atom. It accepts that atom, and then it internally it does a conversion that probably looks something like this, like I did here. It's something like that, and it affects that transformation. So it's an equivalent operation, but it's subtly different. To pass something through PAT, which is the root atom of the whole system, does it basically genericizes the information as much as possible. So we have some syntaxes that PAT is the one that we use almost everywhere because it's convenient to talk about atoms, and whenever we define a function, for instance, we're often talking about atoms. But there are others as well. So I could talk about a ket, which would be a cell. There's a lot of these single shorthand that refer to a particular structure here. So ket would refer to a cell. So I could say, cellify something that is a cell, which makes sense. Like whatever it is, it has to already nest inside of this. So it's we're not saying anything profound by doing this in this particular case here. But there is tar, which is actually a noun. And tar actually throws away all type information, except that this is like a knock statement, essentially. Okay. So tar is the most generic way of expressing any value. It is a noun. And then a noun, of course, can be an atom or a cell, right? It can be a raw value or a cell. But if you're just saying something is a noun, you're throwing away all the type information. And now you would actually have to figure out how to recover that if you wanted to do something with it. We're not going to do much with that in Hoon School, but when you start transmitting information over the network, ship to ship, this is actually the way it gets transmitted. It gets transmitted as raw nouns, and then the types get reapplied on the other end. Now, there's a subtle thing here. Another, we love subtle things. We love to talk about these subtle things. What is this value here? Right? I didn't do this last time, and I probably should have, but try to type the value 1000 in your Dojo right now, right? And what happens when you get to 100? It won't let you type another zero. Yeah. Yeah, so essentially the Dojo will not let you type invalid Hoon code. And the reason that is invalid is because this is actually the correct way to write 1000. It uses the German style dot separator. The reason for this originally is that every atom expression in Hoon is URL safe, and so it could be used for like in a URL expression if you were building things that were going to get interpreted that way. And commas are kind of sketchy because they can carry certain meaning, like separating arguments and stuff. So the decision was made to use the dot, the German style 1000 separator for these values here. So this value here is actually 143,670,796,621, which is the decimal expression for whatever the underlying binary is for the ASCII of this particular value here, which I could actually ask for. Let me see. I think it's going to make me do a bucket to do this correctly. Let me give it a pat T and a pat UX and see if it's happy with this. No, it's not happy with that. I'm going to do. Actually, I'm just going to do this the easy way because I'm running out of time, and I want to make sure to ask questions. So this is the hexadecimal. This is the decimal. This is the binary form of the same code ultimately, right? The text that we're interpreting as Mars exclamation point. Right. So, and actually, if I were to type something else, like something that started with 0B, I can type 1, but I'm unable to type 2 or 3 or 4 because that's not a valid part of a binary, an unsigned binary expression. So that's what's happening there is it's limiting me from doing that. And I'd have to type a dot to separate groups of 4 because that's by convention what it expects, separating those. All right, we are at a good point. Let's see, we talked about gates. We didn't directly talk about generators, which are going to be the first way that we're going to start saving code. Let me see if I actually mention mounting and committing. Yeah, I don't think I go quite deep enough into that yet in the code. Okay, so what's going to happen? The reason I'm prefacing this here, what's going to happen in the homework is it's going to ask you to start writing what's called a generator file. A generator file is really similar to a gate. Like we have this gate, this is this bit of code, it's a function, we attached a name to it. It's similar to that, except instead of saying tis greater than 1, we're just going to save this code in a file. And then we're going to be able to load it and run the code. So this is when we start doing things that look like scripts. Now, what's a little bit of a pain that when you start doing this for the first time, you have to get used to synchronizing your Urbit file system, what Urbit knows about, with what your host operating system knows about. If you haven't done this before, it's a little bit unusual. It's similar to the way that you have to tell Git about the contents of a repository if you're going to share something with GitHub, or if you've used a cloud system that requires you to synchronize files between two things, Hadoop and some of these other things do it. Essentially, we're going to have to tell Hoon that a file exists. We're going to tell your Urbit ship that a file exists, and then anytime we make a change to that file in our text editor, we're going to have to tell Urbit to update its copy of the file. It's really similar to saving or committing to a Git repository if you've worked with GitHub previously, but it is an additional step for you to get used to, that you have to synchronize what Mars, what Urbit knows about with what Earth or Unix or Mac or whatever knows about. So we will give you some instructions in the lesson notes on exactly what that looks like. I think it actually would be good for you to try to walk through it at least once without help. Try it once and see if it makes sense for you. And if you run into any problems with it, ask us in Hooniverse or drop by office hours, and we are perfectly happy to solve that problem for you. But give it a shot with the way that I describe it in the notes when we start talking about generators. So I will email all that to you tomorrow. Now I need to, let's see. Jack, are you able to field questions for just a moment, a Q&A here at the end? And I need to set up a copy of the feedback file really quick, which I was going to do earlier today and neglected to do.
Yep, I can do that.
Okay, so questions for Jack, and then I'll get this set up and pasted for you.
Is there like function overloading or an equivalent, or I guess not function, is there gate overloading where we can write, for example, with the add, I found myself wanting to try to add 3 numbers together. Is there like, could I write an add that can take 2 numbers or 3 numbers or an arbitrarily long collection of numbers and then just sum them?
Yeah, you can write a gate that does that for sure. Is the question like, if you name it add, what's going to happen? Is that your question?
Or I guess I could have like, could I write like a my add that can take anything and then just will sum over it regardless of the, does that make sense?
Oh, and then, yeah, so I guess what you would have to do is you'd have to like put it in your, either you'd put it in your local version of like hoon.hoon, which would be more difficult, or you could make it a library file.
Yeah.
So you could put my add in your library file, and then you can import your library file at the top of like any piece of code that you want to write.
That's
And then-
actually really dope.
Yeah.
Cool. So
Can I
there
show
is
you a
like,
really-
it's kind of like a function
Yes.
overloading feature.
Can I show you a really cool thing with this? We can actually do some really, really fun, powerful stuff with this, because it turns out that, so there are things you could do, like Jack was saying, with, modifying your actual Hoon source code with, like replacing a function or something like that. As far as the names go, and this isn't exactly overloading, it's more like aliasing. Like you run into this problem sometimes in a language like Python, like when you name something list. This is something beginners do, where they're like writing their Python code, and they come along and they're very happily like, my list is 1, 2, 3, and and then now list doesn't work because list is a type that's built into the system, right? So you can break things this way. So this is kind of neat because I can tizfaz, and I can actually name a value. Let me name it 1000. Give it the value 1000. So I actually just named add 1000. Okay, and then I decide that I want to do something clever, like I want to add 3 to that number, right? So this is going to fail because and the way it expresses it here is it says it can't find something at the address to. We'll get into that more, I think, in 2 weeks about why it says it that way. But the neat thing is that because we're doing a depth first search for names, we can tell it to skip the first match that it finds and use the second match that it finds, which means that we can overload anything as many times as we want. Like we can alias things. It's not exactly overload. We can alias things as many times as we want. We just skip it until we get the match we are actually interested in. We're actually not overriding it in the system. We're not even shadowing it. We just have to keep track of the fact that there's 2 names in our names. I mean, this is like a terrible example. I don't write code like this, but it's actually very common in Hoon to talk about something that's like a text that is, like if we had a type that was text, we'd actually say like, my text is text. And then I can talk about my text. And if I need to talk about the type of my text, I would use I would skip the match. Well, let me do it here. But I would be able to skip the match with cat like that, which just skips a match. Really neat, and it's kind of like way deeper lore than you ever want to do in school life.
Is that kind of dangerous in case the like sort of namespace environment you're in changes and you've imported something else with another text, and then you have 3 texts, and so you're accidentally skipping 1 fewer than you thought? Never mind. It doesn't. I'll run into it if it's a problem.
No,
Well, you can't.
Actually, I was going to
It
ask. I actually agree. I'd love to hear kind of the response from that.
So it doesn't, because anytime you import something into your namespace, Hoon resolves everything in what's called subject-oriented programming, which means whenever you write an expression, it's evaluating against what it calls its subject, which is basically the context of code that it has. This is similar to scope in other programming languages, but it's more transparent in many ways. And if you do something like alias a name in scope, then you just lost the name, right? Like you can't access it again.
It's shadowed.
Right? If I name something list in Python, like, oops, I just broke list. If I name something list in Python, like, oops, I just broke list, and I don't know what the ramifications of that are going to be. But if I import something, if I import a set of names like a library for me to use, I can always resolve it against the context of that library or that particular collection of names. So I think without examples and without like knowing more code, it's going to be hard to get deeper into that at at Hoon School lesson 2
No, it
today.
makes sense though.
But it works really well. And it's kind of a fun thing that you can do in Hoon that's really hard to do in some other languages. It's very lispy in some ways.
Yeah, I've never done any functional programming before, so I really wouldn't know what that's like, but I'm looking forward to learning more about it.
Yeah, that's a neat example, and there's actually some really cool things we can dig into going deeper there. So, all right. If I've created my own Hoon program with my own library elements and I pass that program to another ship to either interact with or edit, I must pass along the library files too, correct? Yes. So we're going to distribute things in a way that looks like branches in GitHub, where people are pulling in a specific, version of everything. They're called desks in Clay, but it's a similar idea. So you'll distribute code as an entire collection of files. So
Is there like a Hoon version of like cargo like Rust has, or like pip like Python has, where there's a centralized sort of repository of libraries that we can pull from
no,
in an easy fashion?
the whole game is decentralization.
Okay.
So you actually have to know where you're pulling something from.
Okay.
I think we actually don't have good scripts around how to keep libraries synchronized yet. Like what should the practices for that be? Because a lot of people put libraries on GitHub. And so if you're going to distribute your code, you're using the library version of the library that you pulled from GitHub. And this is fine, but if they make updates later on, you're still distributing the old version, which works with your code. But it's sort of like not clear exactly what the right way to handle that is from a social perspective, in a sense, like the sociology of programming. Anyway, yeah, we're over time. This is good though. I like this discussion. I should probably wrap too, though, and I think it's late for Jack. But thank you all. I'll get the notes posted to you tomorrow, including the generator stuff. Thanks, Jack, for teaching the tree and sugar and mold stuff. And we'll see you in office hours.
Thank you.
Thank you. Good night.